Hello, good afternoon, everyone. My name is B. Abhinandu, and my roll number is 21951A3302. My tech talk concept is about joint mass and density functions in probability and statistics. Let's check one over. Probability, mass, and density functions are used to describe discrete and continuously probability distributions, respectively. This allows us to determine probability of an observation being exactly equal to target discrete or within a set range around our target value. PMFs means probability mass functions and PDFs means probability density functions are important to understand as well expand our knowledge to common statistical distributions. Let us look at probability mass functions for discrete random variables. The probability mass functions provide the probability distributions for discrete variables. For example, rolling dice, there are 6 distinct possible outcomes that defines the entire sample space, that is 1, 2, 3, 4, 5, and 6. Note that we only have whole numbers, that is number 1, 2, or 3 to 5. In the PMF, each discrete variable is mapped to its probability. In an ideal situation, rolling a die, each of 6 variables have 1 by 6 probability of being rolled. Here we can see the probability distributions of 100 throws of a die, 1000 throws of a die, and 10,000 times when a dice is thrown, and 1 lakh times when a die is thrown. Idealized dice outcomes would be displayed as shown in the below. While the ideal distributions of while the ideal distribution of 1 by 6 for each possible outcome 1 to 6. This rarely occurs in real world scenarios. If we simulate an increasing number of trials, we see that the distribution doesn't match the ideal even with 100 dice rolls. As we increase the order of magnitude, the simulated distributions approach the theoretical PMF, as we can see like this. Expected value. The expected value provides the anticipated value from the resulting probability distribution, and it is calculated by multiplying each value by the probability of getting that value and summing for all the possible outcomes. E of x describes the probability distribution. Mu means mean, the average. We can be represented as E of x. Mu equals to sigma I P of x into multiplication with the value. For our ideal dice, E of x mean, which is equals to 1 into 1 by 6 plus 2 into 1 by 6 plus 3 into 1 by 6 plus 4 into 1 by 6 plus 5 into 1 by 6 plus 6 into 1 by 6 results 3.5. The probability of the outcomes is the same, then the expected value equals the average value. But let us look at our 100 throws. From the above we can see that surplus of 4s and 6 thrown, and if we populate the expected value equation, we get the following value: 3.5. E of 0.19 plus 2 of 0.13 plus 3 of 0.14 plus 4 of 0.19 plus 5 of 0.12 plus 6 of 0.06 into 0.23 equals to 3.61. Let us look at variance. Variance measures how far spread are the values from the mean. Formally, the average of the square difference. The variance is nothing but T of x minus mu square, where sigma square equals to sigma I P of probability into x minus mu of whole square, where x equals to the observation, mu is mean. Variance, let us look the variance. Variance equals to 0.19, as we can see 0.19 is the probability and 1 is the first observation minus 3.61 is the mean. And for the second observation, probability is 0.13. 2 minus 3.61 whole square. As we do for all the observations, for all the 6 observations, we get 3.26 as the variance value. This 3.6 value results the variance average spread from the mean. Okay, this seems about right considering in our PM for 100 throws there were an above average number of both 1s and 6 which are far away from the expected value. There were a lot of 4s as well as, but those are fairly closer to the expected value, so it doesn't influence the value as much because we are squaring the difference. Now let us look the probability density function. In probability density function, also or PDF, is for continuously random variables. Now that we covered discrete variables in the probability mass function, then what about the continuous variables? These are the variables that do not fit in fixed amount. That is, it can't be defined in fixed range. Height, for example. Let us look at an example. You can be 6 inch tall, or if you have the most accurate tape ever made, it will be 6.1248938 inches tall. A key aspect of continuously variable is that there are infinite number of possible outcomes. The probability density function shows where the observations are more likely to occur in the probability distribution. Perhaps the most important thing to remember to understand probability density functions is that probability of any specific outcome is zero. We have to think in terms of bins or range of value of calculate the probability of seeing those values. Why is that? Basically because your height is never be exactly 6 inches. It could be 6.00001 or 5.9999. We use a range of values instead because we can calculate the probability that height is between 5 inches 11 to 6 inches 1. This spread is called the interval. We use probability density functions to calculate probability by looking at the area under the curve for our interval. Mathematically, this is why a single point has zero probability. The area of the point is zero as we know that. Because we have continuous variables, we use integrals to calculate the area under the curve between our interval with the following equation. As we know that p of a less than or equal to x less than or equals to b, that a and b are fixed intervals, boundary intervals, and is equals to integration limits from a to b f of x dx is greater than or equals to 0. Here greater than or equals to 0 implies the area will never be in negative. So it must be always greater than 0 only. Plugging in our interval range to the above integral, we calculate the probability of an observation being within the interval of our function. Next slide. The expected value would be, we can calculate the expected value for a continuous variable just as a discrete one. We just switch out the summation occurs across the range for an integral to calculate the area under the curve for entire range. E of x, which is mean, the integral is taken from minus infinity to plus infinity, p of x into x dx. It gives the expected value. Expected value is nothing but mean. Let us look over the variance. Again, we are utilizing the same formula as per discrete random variables, but substituting an integral for the summation because we cannot add an infinite number of points. E of x minus mu square equals to sigma square. This implies the integral, it gives the variance Integration between minus infinity to plus infinity p of x, x minus mu whole square, and d of x. This gives the entire variance of the probability density function in continuous random variables, that is in limited unlimited range. Visualization. There are few strategies for visualizing a probability density function shown here for the common weight height dataset from the Kaggle. First, we can bin the observations into histogram. This is the simplest but requires some arbitrary discussions making, especially because as the number of bins decrease, you will potential obscure some patterns in the data. Second, you can use a prometric approximation. This sounds fancy, but it just entails you using parameters to define our curve, mainly mean and standard deviation. Thirdly, use a kernel distribution estimation, that is KDE plot, which is fundamental data smoothing method and more accurately follows the raw data. Learn more here. You can also see parametric approach cannot account for the round off tips of the distribution and therefore overestimates around the mean. The Here we can see density estimations, the histogram and parametric fit and KDE plot, and all over are aligned in the same way for the probability density.